First, a few words of respect for the Ukrainians fighting for their freedom and for our freedom. Today, I want to do two things. First, I want to finish the presentation of shared memory. Remember last time we saw regular registers. These are very simple registers where you do read and write. The semantics is through intervals. If you do a read and a write, or two reads, for example, let's say I do a write and then a read. The read will read what you've written if there's no overlap. So that's simple, but kind of nasty and simplistic, right? It's not really that strong. But the algorithms are simple. So we saw algorithm last week using majority overlap. So no failure detector, fail silent. But today I want to look at real shared memory, where when you do a write, it's like instantaneous write. And when you do a read, it's like instantaneous read. So the semantics, whenever you do a write, it's as if it's instantaneous. Whenever you do a read, it's like instantaneous, globally. That's what a linearizable register is. It's also called atomic. Those are synonyms. Atomic register or linearizable. There's a weaker version called sequential consistency, where it's only doing on each node, like it's a single memory. If you have read and write on different nodes, then we don't care. So I want to show that. All of this is still in the part of the course where we talk about small systems with fixed number of nodes, like database and cloud, for example. But today also, I'm going to start the second part of the course, where we talk about large systems, where we can have thousands or millions of nodes, and the number of nodes is always changing. New nodes are coming in, leaving, and so on. So this part of the course, these algorithms are very important, of course, also for internet. But you can imagine it's not so easy, so we're going to be a little bit less precise. And also there's still a lot of research going on in this area. Many things are not known yet. So I'm only going to give you some highlights. Today I'm going to talk about gossip algorithms. Okay? So you'll see what that is. Where nodes talk to each other randomly. And work gets done. Nodes are randomly exchanging information, talking to each other, and all the nodes are doing like that, and somehow the work gets done. This is like how the country of Belgium works. Everything happens in the hallways, people chatting, finding compromises. Somehow the country runs. Well, it's like that. Okay, let me finish shared memory. So let me very quickly talk about regular registers. Let's see, I just want to do one slide. Okay, so just to refresh, because we're going to talk about linearizable registers today. Just to get your memory back on what we saw last time. You have read and write. So here's one register. And registers are shared, so that you can return many nodes. And any nodes, in principle, can do read or write. And a regular register has two operations. So a write and a read. And they're intervals. So I do a write, but it's not instantaneous. I need to know, somehow it tells me when it's done. It takes some time. I do a read, and it takes some time. So I have invocation and response. And it's only simple when they don't overlap. Okay, these two intervals. When they overlap, then it's a little funny. the value can be somewhat different. Okay? So databases, all distributed databases like this, they just have millions of registers. Okay? So this kind of algorithm is used for distributed databases. Okay, so those regular registers. So we saw an algorithm for that. Using majority voting, very quickly. Majority of correct processes, and it's a one-end algorithm, so one node is right. But today, I want to go to really, truly single storage, and as usual, it's like a magic trick in the distributed systems. Somehow, the system is going to behave like it's really a single system, even though it takes a long time for messages to go between nodes. But when you do right, it will still be as if it's instantaneous. It's interesting, huh? How is that done? So I'm going to explain to you the magic trick. Okay. First, I want to define what it means. Okay. So there's two kinds of these single system shared memory registers: sequential consistency and linearizability or atomicity. These are safety properties, by the way. I will talk about liveness a little bit later. So sequential consistency means if I do a write and if I do a read on the same node after that, I will read what's written, always. And if I do two writes, I will read the latest one. So it's exactly like a computer with one core, okay? But in between the nodes, it's not like that. I can do a write and a read later on another node, and maybe it will read an earlier value. That's okay for sequential consistency. But linearizability is the real strong one. We have a true global time. So it's as if there is a true global time. If I do a write on one node, then the read on any other node, if it happens after, we'll see that value. How is that done? Of course, it's a magic trick. Yeah? You will see how it's done. Okay? Like with partial synchrony, we're going to play tricks with what is known and what is not known. The point is, you do a write at an instant. This is true. The point is, you don't really know when that instant is. That's the problem, okay? But still, the instant exists. So here's an example. This is an execution. I do write on P1, two reads on P2, and I read 5, and then I read the earlier value, 0. So in a regular register, this is allowed, because when there's an overlap, you can read either the last value written or a previous value. Okay? So this is okay for regular, but it's not okay for sequential consistency, because these two are on the same process, and this read is after that one. And clearly, if you read a 5, there has to be a 5 in there in that single system, so this read cannot read a 0. So this is not sequential consistency. Okay? But sequential consistency and regular are really not comparable. You can't say one is stronger than the other. They're just different. Okay? So the same for atomicity. Atomicity is a strictly stronger property than sequential consistency. Yeah? So here, the two are the same node, and this one is after that one. Can't happen. It's not allowed for atomic registers. Okay? Now, what about this one? Again, this is a good regular register execution because they're overlapping. Now, in this case, sequential consistency will allow it because they're on different nodes. And the time can be different on the two nodes. So if I would do another read on P3, then I would have to read 5. But the time on P2 and P3 are not synchronized. They can have different timelines. Okay? So that's okay. Even though, yeah, there's a clearly happened correlation. Now, in this case, the strong one, atomicity, will not allow it, because now it's global. If I read a 5 here, this one's after. I have to read a 5, because I have now a global single storage. Okay, so that's the strong one. That's the Holy Grail. Okay? Now, just to show you that sequential consistency and regular register are not comparable. You can't say one is stronger than the other. Here's a case where it's okay for sequential consistency, but not okay for regular registers. Because here I write 5, and I end here, and I read 0. So clearly they don't overlap, so I have to read 5 here, but I'm not reading a 5. So it's not regular, but it is sequential, because we can still slide the timelines here up. Maybe the 5s only start appearing later on P2. So it's okay for sequential consistency. Okay? Okay, so those are safety properties. And when I give the algorithms, I'm only going to be talking about the safety properties. But liveness is important too. So I have one slide on liveness. Okay? But you could say a lot about liveness. So I'm going to give you several versions of liveness. So the liveness is also very important. And the algorithms can be live or not alive. Okay? So I'm going to give you 3 versions of liveness. The strongest one. So these are the actual formal definitions. And they have sometimes funny names, as you know. This one is called, the strongest one is weight-free. Okay? So that means that if I have a bunch of nodes running, that all nodes are going to make progress. That's reasonable. That's nobody's stopping things. No deadlocks. So you know what a deadlock is, a cycle in the resource graph. But there's also a concept called live lock, where the 2 nodes are actually doing something, but they're not progressing. Like if 2 people are going through the door, and there's someone, I open the door and there's someone standing there, and I move to the right to let that person pass, but that person moves to the same direction. So we still are in front of each other. And then we do like this again. So we're like dancing, okay? And both algorithms keep doing that. So they're working, but they're not making any progress. So that is called live lock. It's a kind of starvation. But in weight-free, that doesn't happen. Okay? Everybody is making progress. You know when you open the door, you have to step to the right. The other guy also steps to the right. And everything is good. Okay? The second one, a little bit weaker, is called lock-free. Okay, so I did not invent the names. This is a little bit weaker one. It's also called non-blocking. And the point is, at least one node is making progress, but maybe other nodes are not making progress. Okay? Maybe a bunch of nodes are starved, but one node is somehow making progress. Okay? And the weakest one is called obstruction-free or solo termination. Here, one node will make progress if you don't interfere with it. So interference or contention is when 2 nodes are somehow using the same resource. Even though it's not a deadlock, they're still running, okay? So it might be a live lock. Okay, so to give you some intuition, I like to think of these 3 in terms of games or sports. So the weight-free is like running a marathon. It's all individuals. And they're all running, and no one is stopping you. Everyone's making progress, everyone's running. Okay, fine. But the log-free is different. It's like a bicycle race, Tour de France. I have teams competing with each other, and in fact, only one node in the team is supposed to be the winner, okay? That's enough for the team to be a success. And the other nodes might help that node. So the only real condition here is that one node is making progress in each team. So it's not the same as a marathon. And there's another one, obstruction-free, is there's interference. Now we can have interference. So I'm playing football, soccer, trying to get the ball in the goal, but someone is blocking me, and I'm moving this way. That person is very smart and fast and is blocking me. So that's contention, interferes. So that person interferes, maybe I don't make progress. But if he doesn't interfere, or I'm faster, then I make progress. So a node executing without interference will make progress. So those are the three kinds of life, just to give you an idea. And there's lots of discussion. You can find formal definitions and stuff. But I just want to give you an idea. So in the rest of the lecture, I'm not going to talk so much more about liveness. It'll be mostly about safety, but we're assuming that there's going to be life, that there is liveness. Okay? Okay. So let's make now a more precise definition of atomic registers. So we have several properties. So as usual, we're going to have properties. First one is termination. So each read and write eventually completes. So that's weight freedom. That's a liveness property. But now we have safety properties. And this is what makes it special. This is called linearization points. So when I do a read, the result is as if it was immediate, so instantaneous at all nodes at some time between the invocation and the response. So there's still an invocation and a response. But this is only for defining intervals. So when I do a read, it's as if it was instantaneous at some point. Which point? I don't really know, as usual in a distributed system, but there is some point that exists. Okay? And the write happens as if it was instantaneous at some point between invocation and response. So the whole point is we want to make an algorithm that guarantees that. Okay? And if we do that, then we have actually a true single system. Okay? We can also have failed operations, as usual, nodes can fail. So they either completed everywhere or never completed. So exclusive OR means it's only one of these two. It's either this one or that one, but never both. Okay? So that is the definition. It's as if it was instantaneous. Okay, so that's an interesting definition, but we can make a variant of that. We can kind of tweak the regular definition of regular registers to make them work for linearizable. Okay, so here on the left is linearizable, so the immediate, instantaneous. Here on the right, I have this top part is the definition of regular. So the read returns the last value written if it's not concurrent with the write or not concurrent with the failed operation, so no overlap. Otherwise, it's either the last value or a concurrent value that's written. Okay, so this will be the same as read regular. And if we add this condition, we add an ordering condition, then we get the same as this instantaneous. If I read R1 and later on I read R2, then it must have been the case that the write of R1 was before R2. Okay? It could not be. So the ordering is respected for all reads like that. Huh? If the read is before the other read, then the write is before the write. So it's basically a question of consistency, a consistent ordering of all the reads and writes. If such a consistent ordering exists, then they are linearizable. But let me give you some examples to show you kind of how it works. So here is a simple example, and I'm going to prove some property. So the question is, so here I have 3 nodes. I do a write of 5 here, a write of 6, I do a read of 6, and a read of 5. And you can see how it's overlapping. So the question is this atomic? Is it as if there were instantaneous points? So that's kind of hard to realize. You might think, well, maybe not, because here I'm reading a 6 and afterwards I'm reading a 5. So, but I want some kind of a proof. I want a proof that no linearization points exist. Okay? Well, with the ordering, I can make a proof. So here's how it's done. So I cannot find linearization points. And the way to prove it is to prove constraints, to look at constraints on where those linearization points should be. Okay? So the write 5 should happen somewhere here, some instant. So this W5 represents that instant. Okay? The read 5 happens somewhere here. So clearly, the instant that the write happens has to be before the instant that the read happens. So even if I don't know where it is, I know that W5 has to be less than or before read of 5. Okay? Now, I do a read of a 5 and a write 6. Well, if these are single system images, if I do a write 6, clearly if the read is after, it has to read 6. So it's reading 5, so it has to be before. So the read 5 is before write 6. So wherever that instant is, here, it has to be before that. It's possible, The read 5 might be here, and the write 6 might be here, because there's overlap, So that's a condition, it's a constraint, you see, on where those linearization points should be. And also I do a write 6, and now a read 6. So clearly, if I read 6 in a single system, it has to be written before. So the instant that I do the write, which is this number, somewhere on this interval, has to be before the read. That's possible, Maybe I write here and I read here, So it's definitely possible. So this assumes, I can deduce from here, that the instant that I read 5 is before the instant that I read 6. But if I look at these two non-overlapping intervals, I can see that the instant that I read 6, okay, which is somewhere on this interval, is clearly before the instant that I read 5. So there's a contradiction. So I have proved that the linearization points cannot exist. You see how I'm going down from these nebulous virtual linearization points, which, how do you find them? But I can show, but they have to have some order, these points. Okay? They have to have some order, and I can reason on that. So I've proved here, mathematically, that they cannot exist. These linearization points. You might think it's, how do you reason about these points? You can reason about them by assuming that they exist and reasoning about the order. Okay? So this is not an atomic behavior. But now I do a different version. So now I'm doing this version where both reads are reading 6. Okay, slightly different. And now let me show you some linearization points. So this line here, all the instants, I will put them on this line. So let's say I do a write 5 there, a write 6 at that point, a read 6 after, and another read 6 after. Okay? So clearly, I have 4 instants in time, and if I have a single system here, then the read and write is correct. So this is a solution to the problem of finding the linearization points. Okay? So now I have another example. Write 5, read 6, and the previous one was 6, 6, 5, 6. So I have a 5 here, 6, and 6. So here also it's good. If you do reasoning on the order, you will see that it's consistent. Okay? So you can see that this notion of linearization points is actually reasonable, and they can exist, okay, these points, if the ordering is consistent. Okay? Okay, now let's move toward an algorithm. So we want an algorithm. So the main algorithm I'm going to show you today is this NN, linearizable. So it's like the Holy Grail. This is the full one that does everything. Okay? As long as the majority of nodes is correct, this one will do linearizable registers. Okay? Okay. Remember last time for regular registers, we did majority algorithms. Well, and that works for regular registers because of the overlaps, but it doesn't work for linearizable anymore. Okay. So here is an execution similar to what we saw before. Write 5, write 6, read 6, read 5. And remember how the majority works? You write to a majority and you read from a majority, and they have to have a non-empty intersection. Okay? So here I write to a majority. Here I'm writing, but not yet. The write 6 has not yet worked. The read is read from a majority. Okay? So the write is not finished here yet, is not finished, is not actually acknowledged. So I'm actually reading 6 here. Sorry, I have the write here, but here I have the 5 still. Okay, the 6 has not arrived there. Okay, so I read a 6. Okay, and now the write somehow is very slow getting to the majority. This read is quicker, so it's actually going to read 2 5s here. And because even though this write 6 happens, okay, fine, and then the write 6 will happen a little bit slow, but eventually it happens. Okay, so this is a consistent regular register, but we saw this is not atomic. So these majority algorithm doesn't work anymore for atomic registers. It's because now we're worried about instants. Previously, we had only to worry about an interval for the algorithm, but now we have to worry about instants. Okay? So I'm going to show you the fix for this. So I'm not going to actually show you the proof, but because we don't have time, but you will have an intuitive understanding why it's correct. Okay? So the main idea of this algorithm, so we want an algorithm that is correct for linearizing. So the main idea is that when I do a read, I will also, the read will do a write, okay? And that means that any later reads will have to know that what happened in the previous read. So that will kind of force it to be linearizable. See, so if I read a 6, I will make an algorithm that will do a write before doing a read, and then that will force later reads to be consistent. Okay? So that will make the read be slower, okay? And it will be slow enough that that the linearization points can be found. Okay? So that's kind of the idea. So if I make when I do a read, I will do a write to majority before responding. And doing a write means I need to write to a majority. So I'm actually doing a write, okay? So the read will be a lot slower, and any later read will be, of course, reading what was written. And so I will have the linearization point. Okay? And so why does it work? Well, I'm just going to give you kind of the intuition of why it works. So remember, this is the second definition of linearizable. The definition based on order. Now, there was a definition based on linearization points, but if you reason about these points, you can see the important thing is the ordering. So we add this condition. Remember, if we read R1 before, and then we read later on R2, then there must have been a write R1 before R2. But if the read is actually doing a write, then we guarantee that, okay? So in some sense, so a read makes a write, okay? In our algorithm, when we do read operation, it's going to do a write. That means if we later on do a read, we're going to at least see the thing that was written, okay? So we have this condition will be satisfied. So you can kind of say, since we're imposing order, that we're using causality to enforce atomicity. We're imposing the order, okay? So this is the one-writer algorithm. This is called the read-impose algorithm. When I do a read, so the write is like before, majority, but when I do a read, I will actually do a write before responding. So I will read the value from a majority, and then I will do a write to a majority before responding. So that means any later read will see for sure what was written. Okay? So we can optimize this. So there's some neat little optimization we can do. If you do the read, you're reading from majority, if they all have the same sequence number, then actually we don't actually have to write in that case, because the write will not change anything. We will have the maximum, the same sequence number. Okay? So that means the write will have already been done. Okay, and then the final algorithm, the most complicated one that I want to show you. So again, I'm only going to show you the idea of the algorithm. Now assume we have multiple writers. So now we're looking at the NN algorithm. Anybody can write, and anybody can read, and we want linearizable. Okay, so P2 might write, P3 might write. But remember, how did it work, our algorithm? The writer had a sequence number. Whenever I do two writes, and then I do a read, it's the one with the latest sequence number that wins. And the reason is because messages can be slow. Huh? Old messages can arrive later, but since they have old sequence numbers, they will be ignored. Okay? But now let's say we have multiple writers. But each writer has its own sequence number that it's incrementing. Well, these don't have to be the same, okay? So the problem is they might have different ones, and the later write might have smaller sequence numbers. So here I do a write 5 with sequence number 30, but here I do a write 6, and the sequence number might be smaller. And so if we're only looking at sequence numbers, it's not going to work. So we need a little bit something more, okay? So we're going to add something more to make it work. Okay? So here it is, I'm showing it, huh? So here is the write 5 and the write 6. But what do I add now? Well, there's another thing I do. Remember when I did the read impose, the read did a write. And that would guarantee the ordering of successive reads. But now, because of the sequence number, when I do a write, I start by finding out what is the latest sequence number. So I read from a majority to get the last sequence number. And then I know the sequence number to find the highest one. And then I can do my write. And then I'm guaranteed to have a higher sequence number than the previous ones. Okay? So you see, so it's like two phases again, huh? So it's a write consult majority, I call it. So each time a node wants to write, first it tries to figure out what is the sequence number. So it reads from majority, and then it can do the write. So you see the algorithm gets more complicated now. So, okay, so again I want to do a global single system image. What happens if I do two concurrent writes and they have the same sequence number? It might be possible, huh? So they both get majority, they get the same sequence number, and they're somehow concurrent. Well, somehow one of them has to be before the other. Okay, so we have to break the tie. Okay, we have to break the tie. So basically, this is a place where we have to do something like a tie break. Okay, there has to be really an ordering. So the sequence number is not enough. If there's the same sequence number and different nodes, then we have to kind of order the nodes. So the one with the highest process ID wins. So the ordering is sequence number plus process ID. Okay? Okay. Remember, we have to get acknowledgements. Huh? We read from majority, we get acknowledgements. Okay? So whenever I do a write, I read from a majority. So I'm sending a message, and I get back the sequence number. So these nodes that I send message to, they have to acknowledge. Okay? What if I get one of these, a very old message from this? What if I get a very old message to read? Do I still send the acknowledgement? So it's kind of like an orphan message, huh? If I get this read from a very old one, with an old sequence number, do I still send acknowledgement? So it kind of seems like an orphan, but not really, because we have to send the acknowledgement. Because otherwise, this guy will not go forward, will deadlock. Okay, he will block. So this one will not run forward. So we always have to send the X. Okay, acknowledgements is something we always have to send in this algorithm. Okay? So let's say we have a slow node writing 5, a fast node writing 6. Both of them wait for acknowledgements, which they need to continue, okay? So the slow one is waiting for the ACKs. It needs the ACKs, otherwise it doesn't finish. The fast one gets all the ACKs. But P1, if it doesn't get the ACKs, then it will never finish. That's not good. So we have to allow the writes to complete. So we always have to send ACKs, even if they have no effect on the value, okay? So that the algorithms can complete. Okay. Okay, so that's it. That's the NN algorithm. So it has two tricks. So first of all, it's assuming a majority of correct nodes. So we're using the same majority idea as for regular registers. And then we're adding these ordering constraints to make it linearizable. So when you do a read, you will do a write. This is what's called read impose. Impose algorithm. I'll point this way. Read impose. So it will do, when I do read, it will do write. And it's write consult majority. So when I do a write, I will ask for the sequence numbers. So it's kind of like a read, okay, but not really, because I just need the sequence numbers. Okay, so this algorithm will correctly implement linearizable registers. It will guarantee that these linearization points exist. Okay. Okay, so now let me finish up on shared memory. So first thing is we have some comparison between message passing and shared memory. So these are kind of dual things. Okay. We have message passing on one side. Message passing, where nodes are sending messages and the nodes don't share anything. And on this side we have shared memory. So I showed you that we can implement shared memory using message passing. Okay? And the only condition that we need is majority of correct nodes, and we can do it. So we can implement shared memory using message passing. What about the opposite? If we have a shared memory, can we implement message passing? See, now I want to go the other direction. Can we simulate message passing in shared memory? If I give you a single core machine, sequential machine, with a shared memory, so all the threads are accessing the same memory, can you implement message passing on this? What do you think? Now, if you kind of have a feeling for implementing, you will of course immediately say what? How could you implement message passing on a shared memory machine? So that machine like this one, a single process, many threads. Of course you can simulate a distributed system, right? So you basically have to simulate the network, okay? So every channel is like a register, but it contains a sequence of messages. It contains all the messages. So when I send a message, I am storing something in memory, okay? And when I receive the message, I basically look at the channel and see if there's a message there. Either I can busy pull, so I can check, but actually I can do smarter than that. The nodes that are actually waiting for messages, I can put them in the channel. Say, node A is waiting for a message, or node B is waiting, or node 3 is waiting. So when the message arrives, immediately the channel knows that node 3 is waiting for a message. So I implement message passing. So of course it's not that hard even to do that, to implement message passing using shared memory. So we can say that they're actually equivalent in expressiveness. Implement one with the other. Okay? So So that's kind of neat. Of course, it's not as, it might not be the same efficiency, but the functionality is the same. Okay? Okay, let me summarize the algorithms we saw. Okay, so shared memory. So we did regular registers. This is the interval semantics. Remember we did several algorithms, centralized algorithms. Then we did a read one, write all with failure detector. And then again, finally, we always want to get rid of the failure detector. We always start with P and then we want to get rid of it. Here we actually don't need it if we use majority. And then we did the atomic register today. This is the instantaneous semantics. And you can get this by adding ordering constraints so that all the reads and writes have enough order so that they have to be linearizable. If I have a read followed by a read, there must have been a write before preceding another write. That's an ordering constraint. If I have enough ordering constraints, then I satisfy that. So I showed you the read impose algorithm. So the read does a write. So that means it's imposing order. Then at the NN algorithm, here the problem is that the nodes can kind of get out of sync. So here I have a consult, a write consult algorithm to get the sequence numbers. Okay? And then it's okay. So if you really want to implement these registers in a database, you can do it. But you can see they require a bunch of messages anyway, yeah? Okay. Okay. Now, let me give some formal definitions. And this is interesting because this will go back and we will now look at executions again. Okay? So I want to give you a purely formal definition with the concepts we saw before. So remember executions, schedules, and the theorem, the computation theorem, causality. So I want to give you a more formal definition. So here's formal definition. So I have an execution. I have 4 events. I have read invoke event and read response event. And I have write invoke event and write response. Okay? So on register X. So A is the response. And here I want to write A into register X. And the response just tells me when it's done here for the write. There's no value. Okay? So a read operation has 2 events, an invocation and a response. A write operation has 2 events, invocation and a response. And, important, we say an execution is sequential if an invocation on node I is immediately followed by a response, and a response is immediately followed by another invocation. So there's no overlap. Okay? No concurrency. It's purely sequential. Okay? Okay? Okay. So now what do we assume? Well, so we have executions, our system. The first event is an invocation, and every node is alternating. Invocation, response, invocation, response. That's very logical. Huh? One operation after the other. Okay? But it might be that the operation is not done. So an operation is pending if there's no response yet. Otherwise it's complete. And an execution is complete if every operation is complete. And it's important because sometimes, because of failed nodes and so on, it might not be complete. It might be partial. Okay? And the final thing, we can talk about preceding. An operation precedes another one if the response of X is before the invocation of Y. That's clear. There's no overlap. Now we can actually formally define linearization. So an execution is linearizable. So we have an execution where we do stuff on registers. It's linearizable if the following holds. So we have an execution E, and we're looking for another execution F. So E and F have the same events. F is not concurrent, it's sequential. So F it does the same as E, but it's sequential. So that's exactly what linearization points means. Huh? That means that every read or every write is separate from any other one. There's only one sequence. So these are like the linearization points. Okay? And then the operations are legal. So when I do a read, the result is the value of the preceding write. That's reasonable, huh? Okay? And also, the ordering is maintained. An operation that precedes another one in E, it also has the same in F. So basically what I'm saying here is that there exist linearization points and the execution is correct. Huh? So you can see how to formalize it. Huh? For the case of failures, partial executions, failures, so if E has failures, we can linearize it if we can modify it, so by either removing a pending operation or adding a response to the operation. So we make it complete. So, and that makes F linearizable. Okay? And then we finish with sequential consistency. So this is the weaker version now, where the nodes have separate timelines. So it's almost the same, except for the time ordering. So the time ordering is weaker. So now I'm only worried about local precedence. So I'm only looking at events that are on the same node. So if X and Y have the same node and X precedes Y, then it locally proceeds. So I don't care if they're on different nodes. So I have the same condition as before. With the linearizability, there's a sequential execution, but the time ordering is only local. Okay? If an operation locally precedes another one in E, then it locally precedes in F. So it's weaker. Instead of global time ordering, we have local. And that's it. Huh? That gives you the full formal definition. So that is to really understand. Huh? So the formal thing is something you can meditate on to really understand it. Okay, so that finishes our discussion of shared memory. And that finishes the first part of the course. Okay? Now, we're going to go to the second part. But I'm not going to start much yet, but which will be on gossip algorithms. So now we're entering a different world where we can have thousands and millions of nodes. Okay? But I'd make a break first. I want to talk about gossip algorithms. Gossip. So this is a very interesting kind of algorithm. There's a lot of intuition there. It's very general. Sometimes called epidemic algorithms. So this has some really important advantage. So if you have a very large system with hundreds of thousands of nodes, and you want to do something, and you want to bootstrap the system, so get it up to speed, get it running, by far the way to start is always with the gossip algorithm. Okay? So they're scalable, they work for a huge number of nodes. The code is very simple, as we see, and they're extremely robust. Okay? They will survive almost anything, and well, maybe sometimes they're not as fast as you want, but they will work when nothing else works. Okay? So gossip is very intuitive. So I have nodes, me. So I'm sitting next to Ali and I say something, and he says, I know. And he tells Cosmin and I tell Talal. So all these guys are PhD students that we had before. So now 4 people know. This is called a push epidemic. So I say to one person, and then me and that other person say each to one more. So it's like multiplying by 2 each time. So you see it can grow very fast. So this is push. I'm pushing information. You can also have pull, where I talk to Ali and he asks me, okay, no, if Poly asks me and I give information, so I'm asking for information, and also we can have it both ways. So there's basically push, epidemic, pull, and push-pull. Okay, so it scales very nicely, and the several very important properties. Each node, the load is independent of the size of the network. That means the network is growing, but the amount of computation per node does not grow. Okay? The network load, the number of messages in the network, is a linear function of the total number of nodes, which is very reasonable. Now if you have 1 million nodes, or 10 million nodes, you'd have 10 times as many messages as 1 million. So it's extremely scalable. And the information is spreading in logarithm of the system size. So typically you will have an S curve. So in the beginning it's exponential, but when you start reaching most of the nodes, it saturates. Okay? So you always have this exponential growth in the beginning that flattens out. Okay? So how does it work? It's very simple. There is periodic pairwise interaction. So every node, every 50 milliseconds, for example, will talk to another node and exchange information or interact in some way. And the amount of information exchanged is small, is bounded. Okay? So if I have 1 million nodes, each node within every time interval, let's say 50 milliseconds, I will have 1 million messages and maybe 1 million replies. And that's it. Okay? And the state of each node, I call them peers, is bounded. So the amount of memory for each node is fixed, limited, and the amount of memory size in the message is fixed. And each node periodically will send one message and possibly receive a message. Okay? And maybe it does a computation. When it receives the state, it will combine it with its own state in some way. So that's kind of the parameter. Okay? Okay, so how does it choose which node to talk to? Well, that's part of the choice when you design the algorithm. So it's basically random. Either it's random among all of the nodes, but usually you don't know them all. You only have a small set of nodes you know, called the neighbors. Okay? So you're choosing a node among the neighbors, and the set of neighbors can change with time. Okay? You do not assume reliable communication, so messages might be dropped. So maybe during one cycle, you send a message that never arrives. Fine. And then the next cycle, maybe it arrives. Okay? So you don't block or anything, but messages could be dropped. Okay? So usually, the time interval for sending messages is going to be long enough that the protocol is negligible. Maybe you have like 1 millisecond to send a message, but you only do it every 50 milliseconds. So the load on the network is usually very small. Okay? So you can see how the algorithms are kind of working. Huh? So first I want to give you some applications. Okay? So there's many applications. I just give you some ideas. Simple one is dissemination. I want to spread information. It's like a broadcast. Okay? I want to spread information. So for example, there was an algorithm that really existed, was used in Denmark for a festival. There were 100,000 people on a field. Every person had a mobile phone. You cannot use regular mobile phone algorithms when you have 100,000 people in a small area. So they made a gossip algorithm where each phone knows a few neighbors. And so the organizers of the festival sent messages using information dissemination. So I get a piece of information, I send it to my neighbors, and so on. And very quickly, everybody has it. Okay? So that's one application. Another application is repair. Here's when you have replicated data. I have several copies of data, okay? And some of them they crash or they get corrupted, and I use gossip to compare the replicas. So the data can slowly get corrupted for various reasons, a message getting lost, or bugs, whatever. So the gossip is comparing the replicas, and if they see a difference, they will fix it. Maybe they take the most recent one, for example, okay? Or you actually can create replicas with gossip, okay? Or you combine gossip with a regular broadcast algorithm. So you use a regular multicast, best effort, but this one maybe doesn't send message to everybody for various reasons, because nodes are failing, nodes are coming in. Now we're talking about 100,000 nodes. Gossip will fill the gaps. All the guys who didn't get the message using this will get it using gossip. So this kind of thing, repairing, is called anti-entropy protocol. It's very common in the cloud software. Also, membership. You have a group of people, they're members, and it's always changing, 100,000, million people. Well, how do you join the group? Well, each node in the group knows a few neighbors, and that's it. And you have a website, so this is a fixed site, which knows some of the nodes that have kind of been stable for a while. So I pick one randomly, and I say, I'm here, and that way you join the group. Okay? So, process I've heard from, process other people have heard from. So basically the neighbor sets are always being updated. So that is managing membership in very large dynamic groups. Or computation, aggregate computation. Okay? Let's say I want to compute the average amount of computation, the total amount of computation being done by all nodes. How do I do that? That's an aggregate, or the average. Or I want to know how many nodes there are in this system, because nobody knows that. I have this huge network of nodes. Each node knows a few neighbors. It's all over the world, and nodes are always joining and leaving. And there's many systems like that. How many nodes are there? Well, you can run an algorithm that tells you how many nodes. Okay? And then a more sophisticated one. An algorithm really does work. Topology. So let's say I want to organize my nodes into a ring, or into a torus, or a square, or something, a tree, because I want to install a database or some kind of a software. I can use gossip to do that for me. Okay? I start with a local view. I see a few neighbors. I exchange that with somebody else's view, and then I only keep the ones that are closest to me. So I know a few that are close, but many are far. But if I talk to my neighbor, I will know more who are close to me. And because the whole thing is exponential, eventually I will know really the ones that are close to me that should be where I have direct connections in the topology, if I want to make a tree or a ring. We're going to see an algorithm called T-Man that does that. So this is where topology gossip is actually doing real important work. Okay? And there are cloud databases, for example, with many nodes, 80 or 100 nodes in the cloud, and the database nodes are not very reliable, and the whole thing is bootstrapped using a gossip algorithm. Okay, so that's not rare. Happens often. So here, there's another technique called hybrid gossip. It's similar to what I mentioned before. Hybrid gossip means I have two algorithms. I have an efficient algorithm, but it's fragile. It doesn't survive crashes. And then I have a very resilient algorithm, but it's slow. So when I do a broadcast, I create a spanning tree. And this is like the algorithm I showed you early on, where I'm creating this tree of all the nodes. That's very efficient. But if one of the nodes crashes, I disconnect it. So that's not very good, it's fragile. But gossip can repair that. So we have hybrid gossip algorithms which are continuously repairing the spanning tree. And that is very efficient. So there's a famous algorithm called plum tree, which is used in cloud databases. So in real commercial cloud databases, so there's a database called React, for example, that uses this algorithm to maintain very efficient connection. You see, it has the sweet spot where you're connecting gossip with some efficient but fragile algorithm. So it's very useful, gossip. And it does many other things. Failure detection, clock synchronization, reputation. So social networks have usually some piece of it is running on gossip. Even though companies like Facebook, they love putting everything in the cloud because they can control it if it's in the data center. But still there are many pieces of social networks that are running on gossip algorithms. And things like BitTorrent is also running on gossip for the file sharing and so on. Okay, so that's the first part. So you see, it's a lot of applications, and it's used a lot. Now I want to tell you something about how efficient it is on disseminating information. So let's make things very precise. We have, these are the peers. This guy wants to disseminate a message. So it has a buffer size B, and it forwards the message. So a certain number of hops time step T, and it has a fan out F. Okay? So you have three numbers: the size of the buffer, the number of hops, and the fan out is how many you send it each time. So depending on those three numbers, you have different behavior. Okay? And I'm going to show you some nice graphs that are related to disease epidemics. Okay? So we have a fourth number, which is the total number of nodes, population. So we have buffer size, hops, T, fan out, and the size. So how reliable is this? How will it get all the information? How many cycles does it need? Remember, a gossip algorithm runs in these periodic cycles. So the information I give you comes from this very interesting book called The Mathematical Theory of Infectious Diseases and Its Applications from 1975. Okay? So this book was actually important during COVID epidemic, but it basically explains how diseases propagate. Okay? So there's different kinds of ways that diseases propagate. So when I get the disease, I can pass it to other people. And maybe I get it and I'm infectious, so I'm contagious. And the first model is infect forever. So it starts with one infectious individual, so this is like the guy broadcasting it, and I stay always infectious. And you can compute the fraction of individuals infected at round R. So here we're counting rounds, so cycles of the gossip algorithm. Might be 50 milliseconds per cycle. So this is the formula. So N is the number of nodes. Okay, F is the fan out, R is the number of rounds. You can see as the number of rounds increases, that this number goes to 0, so this will converge to 1. Okay? So basically, it increases exponentially by a factor of e to the f early on, but eventually it kind of saturates. Okay? And you can, so it has this S shape, and you can compute the number of rounds. How long does it take for everybody to be infected? So it's logarithmic, depends on the fan. How many people I infect? If I infect 100 people, so that's why you want to put people in isolation. If the F is 0, okay, then it doesn't work anymore. But if the F is 1 or more than 1, basically, then you have some very small number, because it's a logarithm of size. So R is very small. So you can see the number of rounds is not big. You can affect huge number. So the gossip is very fast. Okay. So that's the first model. Infect forever. So basically, everybody gets infected and you have this S curve. But another one is called infect and die model, okay, from the book. That means maybe not die, but once I get the disease, maybe I get cured, and I'm not infectious anymore, okay? So each process will communicate the message exactly once. The infectious process remains infectious only one round, okay? In that case, you have kind of a fixed point equation, okay? So you have a recursive equation. Pi is the number of proportion eventually contaminated. So you have an equation, it's pi is 1 to the e minus pi times f. So it depends on the fan-out. So you have some kind of a fixed point. So if f is equal to 1, here, then pi is equal to 0, satisfies the equation. But that's normal, huh? If I am infectious, I pass it to one person, and then I'm not infectious anymore. So there's only one person, so it's 1 over n, which is like 0. When f is greater than 1, and the fan-out is more than 1, then I get some positive fraction. So f equal 1 is kind of critical value, okay? And if f, the fan-out is very large, it approaches 1, and you can make a graph of that. Okay? So it's gossip pattern, remember, but also disease. So here is the f is 1 curve, okay? And so here is the pi. So the intersection, so this 45-degree line, this is the line where that gives you the solution. So if f equal 1, the intersection is here, 0. But if f grows bigger, the curve starts to approach the vertical axis, and you have some intersection point here. And the bigger the f gets, the closer this gets to 1. So you have some stable equilibrium here, okay? So the bigger fan-out, you have some stable fraction, but it's not 1, it's less than 1, okay? And the latency is also logarithmic, but it's funny, it's a log divided by a log of a log, okay? So log of a log is very close to a constant, okay? So this is very similar to log, but theoretically it's less than log, okay? So you can see how efficient the gossip algorithm is, huh? Okay, a few more words on gossip, but I'm not going to say much because I have a few slides here that are just a general discussion. So how peers get to know each other, okay? The more neighbors you have, the more reliable it gets. So there's a trade-off, scalability against reliability. If I have more neighbors, then I'm more resistant to many messages disappearing or crashes, okay? But if I have less neighbors, I'm less resistant, okay? Also, awareness of the real network. So if the real network is some kind of hierarchy, if my gossip should ideally reflect that, that the neighbors in the gossip algorithm should also be close to me in the real world. Otherwise, it's going to be very slow, okay? And then there's the buffer has some fixed size, so when it gets full, I have to manage it. So there's some kind of priority that I drop or things. So that's kind of a general idea, okay? Each process only knows some of the nodes, and it's some kind of a random sample, but there's this behavior called churn. So churn means the total set of all the nodes is always changing. There's always nodes failing and new nodes coming in. So if I have 1 million nodes, and a few hours later, there's still 1 million, but maybe 10,000 are different. And then hours later than that, there's still 1 million, but more are different. So after a few days, there's still 1 million, but they're all different, okay? So when the process forwards a message, it also gives a list of neighbors. So it's important for processes to not just send data, but also to tell other nodes who are its neighbors.
Okay? And then there's some protocols. I'm not going to say, okay, so all nodes are running the same code. There's some tuning, bootstrapping. Okay, there's some protocols which I will not talk about, called Cyclone, Loosecast, Scamp. Okay, let me go on. So that gives you already some idea of efficiency and how to make gossip algorithms. Before talking about actual gossip algorithms, let me talk about how the networks really are in the world. Okay, so the gossip algorithm is running on networks, social networks, for example, or real-world networks. These networks are graphs. They're graphs, nodes, and edges, but they have almost always a very special kind of graph called small world networks, and this affects a lot the gossip algorithms. Okay. So this is important to know, that real-world networks is not just random graphs. Okay? So how do infected processes choose their neighbors? Depends on who they're connected to, but that depends on the graph. So here let me show 3 different graphs. So nearest neighbor is where each node only has a few guys that are close to it. So the processes are like, I have a neighbor it's like a ring or something. Random network means each process knows random nodes that could be anywhere. Okay? And notice there's a difference in time. If I have a nearest neighbor network, so let me make a picture. So if I have nodes, so nearest neighbor network is something like this. So each node only knows that a few neighbors that are close to it. So it's like a long snake. That's the nearest neighbor. But it could be a grid or a cube shape. Well, that's also a nearest neighbor. So there's nodes here. Now all the nodes are, this would be a nearest neighbor. So the nodes are kind of connected across these lines. Okay? This is nearest neighbor. It's the first one. And the speed, the number of rounds here, it's not logarithm. It's some power of n. And it depends on the dimension of the grid. So if you have a nearest neighbor that's like a long snake, the dimension is 1. Okay? If it's a cube, the dimension is 3. And it might be hypercube, it might be a square in a plane. But it's a power of n. So this is much bigger than logarithm. You see, this is very slow, actually. Yeah? Nearest neighbor is very slow. Even here, it's a power of n. Whereas random network, this is what we saw before, the infectious one. The random network, so this is the nearest neighbor. The random one is very different. You have a bunch of nodes all over the world, and each node randomly connects to nodes even very far away. Okay, close or far away. So it's very, very diffuse like that. And this is the kind of node that you see, the network that you see in the infectious disease. So in this case, it's logarithmic. But in the real world, it's not this and it's not that. Real world networks between people or between computing nodes, it's not nearest neighbor and it's not random. It's a whole new kind of network called small world network. And this was a very important discovery made in the 1990s, that the networks of people or computing nodes, or basically anything in the real world where it's like growing, the World Wide Web, they're not random, they're not nearest neighbor, but they are a very special kind of network called small world network.
very special. So the Gauss algorithm is always running on small world network, okay? And if you want to know more, I'm teaching a course called 1115, Reasoning About a Highly Connected World. So real world social networks are all small world networks. But basically any kind of real world network is going to be a small world network. Traffic networks, networks of friends, people that know each other is a small world network. Networks of computing nodes, the hubs of power distribution, anything in the real world will be actually a small world network. And this course is talking about that, okay? But what is a small world network? What is it really? Okay? A small world network is a network that has two things. It has near neighbors and long way connections. Long away neighbors, far away neighbors. It has both. Okay? It has both short connections as long range. For example, the network of your friends. You have friends that are living close to you, in Belgium or in Louvain or even closer. But probably you also have friends who are very far away. Okay? So I have friends who are living in the United States. I have a friend in Hong Kong. I have friends in Sweden. Okay? So, and probably it's the same for you. There are short connections, but also very far away connections. Okay? So, all these kinds of networks, movie casts, there is something called the Bacon number. So you know Kevin Bacon is an actor. You've probably heard of him, probably seen him, who's played in many movies. So there's something called Bacon number. So if you play in the same movie as Kevin Bacon, if you're in the same movie as him, your Bacon number is 1. If you're playing in a movie with another actor, and that actor has Bacon number 1, then your number is 2. Okay? It turns out that almost all actors in the world have a Bacon number of 5 or less than 5. Only very few have 6. And people search for a long time for Bacon number of 7 or 8. And there's some very obscure private Soviet movie from the 1920s, experimental cinema, and there's a few actors in there who have Bacon number 7 or 8. Okay? You can see how obscure it is. So that's very close. The distance is very small. So there's two formal properties of these networks. Small, average, shortest path length. That means everybody is close together. That's funny, huh? The path length between me and someone else, the path is, the distance between me and someone is the shortest path, huh? So that's very small. And secondly, which is kind of contradictory, high clustering. So it's very compact. How can it be compact and also have and everybody be close together? So it's like that. So many of these has these two properties. So random graphs or nearest neighbor graphs are not like that. The random graphs are very diffuse. They're not clustered. Neighbor graphs have large path lengths like snakes. Small world networks have short paths. Okay. So we can go into graph theory. So the clustering coefficient measures how compact it is. For each node, you look at the neighbors, okay? You count the number of edges between the neighbors and you divide by the maximum possible. So if I have a node here with neighbors, node n, some of these neighbors are also friends. So maybe this one is a friend of this one, and this guy is a friend to this guy. So that means my clustering coefficient will be 2 divided by the maximum possible. So if I have 5 neighbors, the number of possible is the number of combinations of 5 elements taken 2 by 2. So that's 5 times 4 divided by 2 times 1 is 10. And if I have 2 neighbors, then the clustering coefficient is 2 over 10 is 0.2, which is small. But usually it's much bigger than that. So the friends of my friends are also friends. So that's high clustering, okay? So you can show, so this is a picture coming, so this was discovered in 1990s. So this is a famous model called Watts-Strogatz model, which defines nearest neighbors. So this is like a ring, huh? It defines random, where the legs are going everywhere. And a small world is like a hybrid between the two. It has a lot of clustering, but it also has these long-range hops. Okay? So the gossip algorithm will always be running on small world. And this gives us this property called 6 degrees of freedom, which means on a small world network, everybody is close together. So this is a famous experiment. So you've maybe heard of this, that everybody is separated by only 6 degrees of freedom. Well, this is coming from a famous experiment from 1963, where you forward letters across the United States from a random person to a random person. People that don't know each other. And the only condition is you have to forward it to a friend of yours whom you think is closer to that person. So it goes from the East Coast, from New York to California, and people that don't know each other, you just have to forward the letter to someone you think is closer. And this is how many letters it takes to get to the destination. You see the median near will be 6, small. So only 6 hops and you get to some totally unknown person. Okay? And so here's a picture of a small world network. You can see there's clustering, huh? It's like compact, but there's also these long range links. Very far links, but also a lot of clustering. So real world networks are always like that. Okay, so that should tell you what the gossip is actually running on. So that means a small world network means that it helps gossip algorithms. It means that it's very easy to cover all the nodes. Okay? So, for example, how many nodes do you think there are between you and President Biden? For me, there's only one intermediate node. Funny, huh? When I was a student, I knew another guy who was a student. Yeah? And he actually became a rabbi in Delaware. And he was doing a service. And Biden attended the service because there was a lady who was a contributor to his funding, his campaign, and he was there to be like, say thank you. So he talked to the rabbi. So between me and the rabbi and the Biden, there's only one link. See how close I am to President Biden. Amazing, huh? So this is typical for a small world network. Okay, so let me now. We're now going to define some real gossip algorithms. And for this, I want to show you a framework. I want to show you the code, how to write gossip algorithms. And this is a very nice framework. It's one of the nice ones, made by 2 researchers called Mark Gelasity and Ozal Babaoglu. So here is the code. This is the whole code. This is the whole code. You see, I like small programs, huh? Each node is running 2 threads, an active thread and a passive thread. Both of them are running infinite loops. The active thread, it does like this. It waits for t time units. So this is the period, the cycle of the gossip. 50 milliseconds, for example. And then it selects a peer, one of its neighbors, Q. It pushes S to Q, so it does a send. It receives a message from Q. And then it updates its local state. So S is its local state. So you see, there's this function, select peer and update, and the type of S, it's parameter. And the passive thread is on the other side. So the passive thread is waiting for messages to come. When someone does a push, it gets a pull, it receives the node that it's getting it from, P and SP, it sends a push back. It's the response, so that corresponds to this pull, and also updated states. So this is the general push-pull.
And that's it. That is the full code. So all gossip algorithms, we're going to see, are going to be implemented by this. So you have to, of course, fill in the blanks. Now, it's a framework. Select peer and update. And also, what is the state? And that's it. Okay? So to instantiate this, you need local state, the method select peer. You have to define whether you do push or pull, and update. And that's it. See how simple gossip is, huh? It's really so simple. Okay, let me show you one kind of algorithm for gossip called aggregation. This is when you want to do some computation on all the data of all the nodes. Okay? So this is push-pull. So two nodes have some piece of information. They exchange information. They each do update. Okay? And S is the number you're trying to compute. So it's going to get better and better. It's going to converge. So it's the current estimate of the global aggregate you're computing. Select peer picks a random neighbor. Update is some numerical function that defines what you're computing. Average or total or some other kind of number. So this converges very fast. So here's a graph. So there's a paper on the Babaglu and Gilassi framework, and the paper is called the T-Man. It's mostly about topology maintenance, but it presents this framework and it shows you how to do this. You can see how it converges. So here we have the number of cycles, so small number. Here we have the estimate. Now we're computing an average. This is logarithmic, okay? You see in the beginning it's very bad, but after 10 cycles it starts getting better and better, okay? And here, after 15 cycles, it starts getting really good. And here we have an expanded version of the part going from 20 to 30. So this is expanded. You can see how it's basically exponentially convergent. The size of this interval is reduced by a factor each time. Okay? So in gossip-based averaging, the variance of the set of estimates decreases exponentially. Okay? So let's go and do something interesting. Let's say that we want to compute how many nodes are there. Because nobody knows. It's this thing all over the world. People are joining, failing, joining. There's churn. How many nodes are there? Of course, the number is fluctuating, but you want an estimate. How do you do that? You can run gossip to do that. So it's a simple idea. It's like this. If you say exactly one node has the value 1, and all other nodes have the value 0, then you run an algorithm to compute the average. And when it converges, the average will be 1 over n. All you do is you invert that and you get an estimate of the size. So, if I have a node here, and a node here, here's value 1, here's value 0. After one iteration, they're both 0.5. But there might be a third node here with 0. And then after one iteration, they're both 0.25. And if you keep going, it will eventually converge. Okay? And when it converges, you invert the average, and you get an estimate of the number. So that's the idea. But it's not so simple, right? How can you guarantee that exactly one node has value 1? Because you don't even know all the nodes. What do you think? So the little red D means, how would you do this? I mean, this is an idea which is nice, and you can make it work, but you have to think a little bit. How do you guarantee that exactly one node will have value 1? What do you think? How would you implement that? Because you don't even know all the nodes. You know a few nodes and their neighbors. How do you guarantee that? Yeah? Ideas? I thought somebody's hand was raised. No. It was just somebody
holding his hand up in despair or something? No. No? How do you guarantee that? How would you guarantee? You have to use some technique, huh? Because you don't know all the nodes. So one way is to take some random bit vector where you are here is pretty sure to be unique. And this identifies value. It's like a dictionary, yeah? Or an array with some key, okay? You can do that. And if you do that, you can be almost sure that no other node will have picked the same one, okay? So we don't need to do any kind of a distributed algorithm, huh? So we have a basic protocol, and we have pairs. We take a unique identifier and the number. And this we can pretty much guarantee it's unique. Even the IP address will be made it pretty much unique on the internet. And the value starts at 0. And you can have several of those. You don't even need one. You can have more than one. And they are propagating. So when I receive a pair, I get that pair, and I keep part of the value locally. And when I see another one with the same unique identifier, I make the average of the values. And I keep running that. And eventually a whole bunch of the nodes will have the unique identifier, and they will have some value that converges. Okay? And you need some scheme to bound the number of these instances, because maybe you have too many and the local buffer is not big enough. So let's say you have a maximum of 30 or something. See how it works? See the kind of thinking you have to do for this kind of algorithm? And this is still not enough, because it can kind of get stuck. You run it, you can see that sometimes it doesn't really converge, because it's not perfectly random or for some various reasons. That there might be some bottleneck somewhere, a path to the network. The network might not be completely well connected the way it should be, so things might get stuck. So you periodically restart the algorithm, and you use the values from the previous, what's called epoch, so you restart the algorithm from scratch. So it finds different paths, it runs again. So if you do that repeatedly, so whenever it converges, you restart the algorithm. Then you get much better values. Okay? You can study why it's like that, because of the network structure. Okay? So here's some results. So we have a network of 100,000 nodes here. Huh? And at each beginning of each cycle, so remember it's running in cycles, huh? 1,000 nodes crash, and new 1,000 nodes come in, so there's always 1,000. Each of the data points here is a converged running of the algorithm. And here is the number of concurrent instances of the algorithm we're running. See, if we have more, it's better. Huh? If we only have a few, it's kind of not so good. But I mean, it's between 95,000 and 105,000, okay? So it's not that bad, but you can see the network is changing a lot. Every cycle, 1% of the nodes crashes, and new ones. So after 10 cycles, 10% of the nodes have been changed. So the network is always moving on. But still, you can get a pretty reasonable estimate of the size. Interesting, huh? So here's another graph. Here in this one, its messages are getting lost. So when I send a message, 20% are lost. That's a lot, huh? 1 out of every 5 messages just disappears. So the algorithm it's a very hostile environment. Huh? Usually in real networks, it's much less than this. Huh? But still, look how close we get to the 100,000 number. Of course, it's not that close. Huh? It's 10% maybe fluctuating. But still not bad, considering how much weirdness is going on there. Okay? So this is the kind of thinking that you do when you do gossip. Okay? And then the final thing, but I'll just introduce it. This is the most complicated algorithm I want to show. This is topology management. This is also something that's really used. So this is an algorithm called T-Man, which was presented by Gelasity and Babaoğlu. And algorithms like this are used in real systems. So if I have a bunch of nodes, and they're kind of just a bunch of nodes, but I want to organize them into a ring, for example. I want to make a database. And the nodes that are closest to each other should be, in the real world, should be close on the ring. So somehow I want to organize them. Or I have a large number of nodes, and this is happening in some of the more sophisticated file sharing things, like BitTorrent style. The nodes are somehow organized because they have to keep track of what are the files to look it up. So they have something called a distributed hash table structure, very complicated structure, but you don't have it from scratch. So there's a gossip algorithm that kind of builds it from nothing, okay? From a bunch of random nodes, it builds this very nice structure. So this is an algorithm called topology management. So it kind of brings the system up from its bootstraps, in a sense, huh? So it can jumpstart protocols. And it's used quite a bit in the real world in things like distributed hash table, DHT, which are used when you have big, large, dynamic tables of data that you want to look up. You can't do that in gossip, doing lookup, because it's all a mess, okay? But the gossip can create a beautiful structure, okay? Okay, so let me show that next time. So next time I will show how to do topology management. So you can see the beauty and the power of gossip, huh? Okay, so I stop here.